Good morning. My name is Ravi Kumar, Associate Professor, Department of Pharmaceutical Chemistry, School of Pharmacy, Nalla Narasimha Reddy Education Society, Group of Institutions. Today's class, we are discussing about benzene and its evidences. Objectives of today's class. Upon completion of today's class, the students is able to define aromatic compounds, explain the structure of benzene correlating with evidences, explain the stability of benzene. Benzene undergoes substitution reaction rather than addition reaction, and student able to write the resonance hybrid structures of benzene. Coming to introduction, the word aromatic conjures pleasant odor. There are so many aromatic compounds which gives pleasant odor. For example, almonds gives a pleasant odor, that is because of benzaldehyde. Cloves, the odor of clove is due to eugenol, and the odor of cinnamon is due to cinnamaldehyde. When you see the structures of different aromatic compounds, the common feature we observe is aromatic ring. Scientists thought that the aromatic ring is due to this smell is due to this aromatic ring, but there are some aromatic compounds which do not give smell or odor, that is aspirin. The scientists found that that is not due to aromatic compounds. The benzene containing compounds are classified as aromatic because not of their smell, they have a special feature, that is aromatic ring. So benzene is a unique, highly unsaturated six-member structure which has specific feature, that is displacement or delocalization of electrons. When you come to the history of benzene structure, in 1825, scientist Michael Faraday discovered a new hydrocarbon from a compressed illuminating gas produced by the pyrolysis of whale oil. He found that the compound found is having a specific feature, that is called as bicarbonate of hydrogen. In 1934, German scientist Mitscherlich synthesized benzene by distillation of benzoic acid with lime. So here benzoic acid, when it is treated with lime, it undergoes a decarboxylation to give a benzene structure and CaCO3. Mitscherlich has also showed the molecular formula of benzene as C6H6. He was surprised by seeing the structure, the molecular formula of benzene C6H6, which is not according to the structural theory, because all the carbons should have four hydrogens. If you take example of alkenes and alkynes, the number of hydrogens will be more proportionate to the carbons. But here in benzene, the number of carbons are equivalent with that of hydrogen. They are in the ratio of 1:1. This leads to the classification of aromatic compounds from other organic compounds. In 1846, Hoffman isolated the same compound in large quantities by distillation with coal. If you see the structure of benzene, benzene was first identified in 1825. The properties of benzene, chemical and physical properties, are more known than other compounds. It is well known, the properties are well known, but there is no satisfactory structure was found until 1931. Why the structure of benzene was not identified, discovered? That is not because of the complexity of the structure, but it is rather the limitations of structural theory, that is resonance concept was not discovered till 1931. Understanding the structure of benzene is very important to study the aromatic compounds and extending their knowledge to structural theory. So to study the structure of benzene, we need to discuss various facts of benzene. That is molecular formula, stability of benzene ring, carbon bond length in benzene, and resonance structure. So we need to examine these facts of benzene with that of various structures produced, discovered at that time. So molecular formula of benzene was found to be C6H6. Benzene always form a mono-substituted product, and benzene will give 3 isomeric compounds when it undergoes a disubstitution product. Benzene will undergo substitution reaction rather than addition reaction. Heat of hydrogenation is lower than expected. The carbon-carbon bond length is equal, and it is intermediate between carbon bond, single bond and a double bond, and the resonance structure of benzene. So these are the evidences we are not going to discuss, correlating with the structure of benzene, which as given by various scientists. When you see the molecular formula of benzene, it is C6H6. Elemental composition and molecular weight of benzene gives the molecular formula is C6H6, but the question comes is how the atoms are arranged. You can arrange the carbon and hydrogen atoms in various structural features, but those structures should satisfy with the facts of benzene, that is chemical and physical properties of benzene. Various scientists have given different structures matching this formula, that is C6H6. In 1855, Auguste Kekule explained that all the carbon atoms join in the form of open chain structure. But he realized that in 1865, they may be sometimes formed in the form of closed rings. So Kekule has suggested that benzene is having a planar structure, cyclic, and having alternate double bonds and single bonds. Along with that, various scientists have given the structure of benzene with a consistent molecular formula. But the committee has finalized only 5 structures of benzene which are very nearer to the molecular formula. So these are the structures of benzene which has given by various scientists. So first structure is given by Kekule, second structure is given by Dever, and other structures are given by other scientists. So we need to verify these structures with that of properties of benzene. The second point is benzene yields only mono substitution product but not other products. For example, benzene, when it is treated with bromine, it gives bromobenzene. Treated with chlorine gives chlorobenzene, and when it is treated with nitration mixture, it gives nitrobenzene only. There is a limitation here that all the hydrogens in the benzene might be same or equivalent. So whenever the benzene is reacted with these reagents, the hydrogen, any hydrogen is replaced with that of this reagent to form mono-substituted derivative. So when you compare these all structures, so in Kekle structure, all the structures hydrogens are same. But when you come to their structure, this carbon hydrogen is sp3 and this carbon is sp2. So there are two different carbons here. So there is a possibility of di substitution. Different products are formed, but not single product. If you see third structure, you have different carbons here, CH2, CH. So there is a chance of two products formed. Similarly, in the fifth structure also, you have alkyne carbon, alkenyl carbon, different compounds may be produced. But when you see fourth structure, CH3 and CH3, they are equivalent protons. So it may give only one mono substituted product. So out of these five, second structure, third structure, and fifth structure were rejected. Only first and fourth structure was finalized based on mono substitution product. So first and fourth are finalized because these two structures are giving mono substituted product, whereas second and third and fifth were rejected because fifth is giving two derivatives, one bromo or two bromo compounds on bromination. Third point, that is benzene yields three isomeric disubstitution products. Whenever benzene is reacted with bromine, 2 moles of bromine, it gives rise to dibromobenzene. When benzene is reacted with 2 moles of chlorine, it gives dichlorobenzene. The point here is benzene gives rise to 3 derivatives, that is 1, 2 dibromobenzene, 1, 3 dibromobenzene, and 1, 4 dibromobenzene. We need to check whether the fourth compound gives 3 isomers. But here in the fourth structure, you have only similar type of protons, so it may not give 3 isomers. So the fourth structure is rejected because it is not going to give 3 isomers. So the Kekle structure was given highest preference for the structure of benzene. On close examination of the structure, there is 1, 2 dibromo structure. There is a chance of writing another format, that is, it can be written in this format also. If you observe that the bromine atoms bearing carbons are different. Here the carbon and carbon are having double bond, and here the carbon is having a single bond. So these two structures are differently arranged. Means Kekule visualized that benzene molecule is a dynamic molecule because there is the displacement of bonds takes place. So he assumed that benzene structure would be analogy of a snake holding its tail and rotating around like this. So he assumed that there is a dynamic thing in the benzene structure. He was visualizing larger atoms very near to him and smaller atoms away from him, and they are rotating, they are modeling before his eyes. So he explained that benzene is having some dynamic thing in the benzene ring. So based on that, benzene structure is not a single structure, it is two structures which are altering each other, As a consequences, the 1,2 dibromobenzene will be in equilibrium, rapid equilibrium, and they are not separated. So here the point is, benzene, when it is undergoing disubstitution, each disubstituted molecule will be in equilibrium. Coming to the stability of benzene, benzene undergoes different types of reaction. From the fact of A, B, and C, which are satisfactory for catalytic structure, but there is some point where there is an unusual stability of benzene ring. When you observe the structure of benzene, you have 3 double bonds. Means it is a structure similar to cyclohexene. Cyclohexene has 1 double bond, and if you see cyclohexadiene is having 2 double bonds, and catalytic structure is identified as cyclohexatriene. Means benzene is having 3 double bonds. So all these are coming under alkenes. So alkenes have a characteristic reaction called as addition reaction. So benzene should undergo addition reaction, but it is not happening. Benzene will undergo substitution reaction. So alkenes, when they are reacted with a electrophile, the electrophile is being added against the double bond, so that additional product is taking place here. But this is not happening in the benzene. Why? Because there is a dynamic thing observed by Kipling. So when you see certain reactions here, KMnO4, when it is reacted with benzene, there is no reaction, but cyclohexene is having a rapid oxidation reaction. When bromine in the presence of carbon tetrachloride reacts with a cyclohexene, the reaction is very, very rapid, but there is no reaction with benzene. Even with HI, hydrogen iodide, the reaction with cyclohexene is very rapid, but there is no reaction with benzene. What the information gives here is benzene is not undergoing addition reaction, but it may go substitution reaction. But when the benzene is hydrogenated in the presence of a catalyst, there is a slow hydrogenation takes place at high temperature and high pressure. But whereas in cycloalkene, that is cyclohexene, there is a rapid hydrogenation at 25 degrees centigrade and low pressure. So when you observe these reactions, so benzene is not similar to alkene, which is having double bonds. So benzene, it undergoes substitution reaction rather than addition reaction. So the question comes now, why benzene undergoes substitution reaction rather than addition? We'll see that. So when benzene is reacted with an electrophile, why benzene should react with electrophile? Because benzene is full of electron cloud. Benzene has to react with a electron deficient species. So when benzene is reacted with electron deficient species, that is electrophile, so what happens? The pi bond donates electrons to this electrophile and form a bond. When it forms a bond, there is a disturbance in aromaticity. There is a disturbance in double bond. So the compound becomes non-aromatic because the double bond is converted to single bond. There is a disturbance in aromatic nature. So there is a possibility of addition product. If benzene is undergoing addition product, the disturbance in double bond system takes place. Means aromaticity is disturbed. But benzene, we know that it is a stable molecule and have alternate double bonds. So here what happens when there is a carbonium ion formed as intermediate. So this carbonium ion, to nullify this carbonium ion, hydrogen atom is leaving the substrate and the pair of electrons which are there is forming a double bond here to retain the complete conjugated system to form substitution reaction than that of addition reaction. So here benzene, when it undergoes addition reaction, the complete conjugation is disturbed, which is against the property that benzene is more stable compound. So benzene, when it is reacted with electrophile, substitution of hydrogen with electrophile takes place to give an aromatic compound. So benzene undergoes electrophilic substitution reaction rather than addition reaction. One more point we need to discuss here is benzene has very low energy. So we know that most of the unstable molecules will have high potential energy. Means stable molecules will have less potential energy. So when you compare here, heat of hydrogenation of benzene is very less than that of expected. Then what is heat of hydrogenation? Heat of hydrogenation is nothing but it is a heat evolved when 1 mole of unsaturated compound is hydrogenated. Means when one double bond is converted to a single bond, there is a heat evolved. That heat we call as heat of hydrogenation. The amount of heat which is evolved is approximately 28 to 30 kilocalories per mole. Means when cyclohexane is converted to cyclohexane, it releases 28.6 kilocalories per mole. So it is 28.6 kilocalories and cyclohexene is converted to cyclohexane. And cyclohexadiene, which is having 2 double bonds, when it is converted to cyclohexane, so it should be double of 28.6. Means it should have 57.2. It should release 57.2 kilocalories per mole. But it is releasing 55.4. It is less than that of 57.2. Similarly, when cyclohexatriene, which is similar to the of Kepler structure, when it is converted to cyclohexane, so it is having 3 double bonds, so the value should be triple that of 28.6, but that is it should have 85.8 kilocalories it should release, but it is releasing only 49.8 kilocalories. Means it is 36 kilocalories less than that of calculated amount, that is 85.8. Means benzene is having very less energy in its system. The molecule which is having less energy, less potential energy, the molecule is said to be more stable. And the molecule which is having high energy, we call as it is unstable. So cyclohexatriene should have 85.8, but this benzene is having only 49.8, and it is having 36 kilocalories less than that of calculated. This energy 36 kilocalories is called as resonance energy. Benzene is more stable because it is having less energy. When you come to the third point, that is carbon-carbon bond length in benzene is same. But we know according to the structural theory, the carbon-carbon single bond in ethane is 1.53 nanometer, sorry, angstroms, 1.54 angstroms. And in alkene, ethene, the bond length, carbon-carbon bond length is 1.34 angstroms. In alkyne, that is acetylene, the carbon-carbon triple bond length is 1.20 angstroms. If you consider these bond length in benzene structure, because benzene structure have double bond and single bond which are alternative in nature, the structure should be like this. The bond CC bond length is long and carbon-carbon double bond is short. So the benzene structure should be resemble like this, but it is not so. In 1891, Scientists have taken scanning tunneling microscope structure and visualized the benzene structure like this. Means the structure of benzene is having similar carbon-carbon bond length. All the carbon-carbon bond length is same in the structure, but it is not displaying like this. Means the carbon-carbon bond length in benzene is same. So it is between 1.54 and 1.34. It is carbon-carbon bond length is 1.38 angstroms. Why it is so? It is because of delocalization of electrons. What do you mean by delocalization of electrons? Displacement of electrons from one carbon to other carbon. Moving of electrons from one carbon to other carbon is called delocalization. So in benzene, there is a delocalization of electrons takes place. Because of that, the double bond and single bond, they are converted to a bond length which is intermediate between 1.38, 1.54 and 1.34. That is 1.38. So benzene is having a bond length of 1.38, which is same in all the carbon-carbon bond length. So previously, Kekule's structure was with doubtfully they have accepted. The chemists have accepted the Kekule structure with doubtful until the discovery of the concept called as a resonance. The resonance concept was discovered in 1931. Till 1931, scientists have used Kekule structure with doubtful because the structural theory limitation was there. So in 1931, the extension of structure theory gives a concept called as a resonance, which said that there is a delocalization of electrons takes place. Because of that, there is a structural isomers produced, which are having similar molecular formula, but they differ in the arrangement of electrons. The structures are similar, but the arrangement of electrons are different. These two structures, 1 and 2, they are similar, but they have double bond position varies. In the first structure, you have double bond between 1 and 2, 3 and 4, and 5 and 6. But in the second structure, the double bonds are present between 2 and 3, 4 and 5, and 6 and 1. There is a difference in the position of double bonds. So the carbon benzene structure will give two hybrid structures which are almost equivalent, but they are stabilized by resonance. That concept is given in 1931. With the concept of resonance, the structure of benzene was finalized that the structure of benzene would be Kekule structure. So there is no evidence to support rapidly changing structures. We know that there is a delocalization of electrons, but there is no evidence. So modern chemists use the concept of conjugation to describe how electrons are delocalized across the whole molecule. So valency bond theory explains that the benzene has unhybridized p orbitals which are perpendicular to the plane of the ring. They are overlapping each other to form a double bond. So they form a double bond and they create an electron cloud above the plane and below the plane. This spreading of electrons, movement of electrons from one carbon to other carbon, stabilizes the molecule. That is the reason benzene is having less energy and benzene is said to be more stable. So these are the structures, resonance hybrid structures of benzene. So benzene structure is the combination of these two structures. These two structures are in equilibrium. The movement of electrons will take place like this. So here this benzene, this structure, benzene pi bond shifts here. When it shifts here, this carbon gets positive charge and this carbon gets bond. So when the shifting of bond takes place here, this bond shifts to the next carbon and this carbon gets negative charge. When this carbon gets negative charge, this will form the form pi bond here. When it forms a pi bond here, this bond shifts here. So the negative charge here and the positive charge here will form a double bond here. So here the delocalization took place and there is a hybrid structure. Benzene has two hybrid structures which differ in the position of electron cloud or position of double bonds, but they have same molecular formula and they have same connectivity. It can be written as hybrid structure by writing a circle in between the aromatic nucleus. Now we'll see there are a few questions which we can discuss. Which drawing most accurately represent the structure and bonding in benzene? Are any of the pictures completely incorrect? If so, which and why? Which representation takes longest to draw? Which is quickest to draw? In your opinion, which picture is best overall and why? So the first question, which drawing most accurately represent the structure and bonding? The structure would be B and C. Why? Because if you see B structure is having a hybrid of both structures, we have drawn a circle in between. And we can represent benzene structure like this also. Which of the structure is incorrect? Why? This D structure is incorrect because it is not having double bonds. Which representation takes longest to draw and which is quickest to draw? This B structure is quickest to draw and this A structure is longest to draw. In your opinion, which picture is best overall? B structure would be the structure which is best overall. So these are some questions which we can answer. So today's class we have discussed about the definition of aromatic compounds and the structure of Kekulé structure of benzene was explained. We have correlated the structures of benzene with various facts of benzene. It is molecular formula, molar substitution, disubstitution, resonance energy, bond length, and reactions. So benzene is a peculiar structure with more unsaturation, planar, and has a stability because of resonance energy. That is 36 kilocalories. We discussed about the resonance structure of benzene, how the delocalization of electrons takes place. So with this, we conclude the class, and these are the references. You can refer Morrison Boyd, Organic Chemistry by Morrison Boyd, Organic Chemistry by I.L. Pinar, and Organic Chemistry by Ball and Ball. With this, I conclude the class. Thank you.